Hello, today we're going to be focusing on the Gale-shapely algorithm, more specifically that we have stable matchings. Now, that's to say if we have two groups of people, and this is n people, and we have another group of n people, so they're the same amount of people on either sides of the group. Let's give these people names. We have A, B, C, and 1, 2, 3. Let's just call this set group A and call this set group B. And they're both n people over here and n people over here. Now, a stable matching is no two pairs, let's go pairs. No two pairs would rather trade partners. This means that, let's say we have this connection over here. Let's make an aside. So this means that we have A and we have B over here, and A is matched with 1, and B is matched with 3. Now, an unstable matching is if A and 3 would rather be with each other. This is not a stable matching. Let's copy this. Let's put it over to the side. This is not a stable matching. Oh, did not mean to change the color. So this is not a stable matching. So now, what if 3 wants to be with A and B wants to be with 1? So this pair doesn't even want to be with each other. They're stuck with each other. If A would rather be with 1 and 1 would rather be with A, then no swaps can occur. If A prefers 1 and 1 prefers A, then no swaps can occur and we have a stable matching. So let me put that back. If this happens, we still have a stable matching. So this is still a stable matching. Change the color again. So this is correct. This is still a stable matching. In the Gale-shapely algorithm, it works like this. There are two groups of people. There are the proposers, and there are the people who accept. There are proposers and there are acceptors. People who accept. By that we mean, in the Gale-shapely algorithm, it takes a group A or group B to propose first. So group A would propose first, and they choose who they prefer, or group B proposes first, and A becomes the acceptors, or they have to accept. So there's n people. Remember, there's n people on both sides. Now, this means in the Gale-shapely algorithm, it takes an acceptor, an acceptor and a proposer. It also takes preference lists. So let's create some preference lists over here. Let's go over and let's create a preference list for A. So A is going to have its own preference list. So we're going to have A, B, and C. It's going to be 3 by 3 since there are 3 people to propose to. And let's say A prefers 1, 2, 3. So this is from most to least preferred. From most to least preferred. Let's say 2, then 3, then 1, and then 3, then 1, then 2. And now let's make a preference list for B. B over here. let's say 1, 2, and 3. 1, 2, and 3. Now, let's say 1 likes A, 2 likes A, and 3 likes C. 3 likes C. And then we have 1 likes B, let's say C likes B, and then let's start filling this out. Let's just start filling this out, B and C. Let's say they both have the same preference list, and then A. So these are both the preference lists. These are both the preference list. Let's move some things around. I hope this part about stable matchings is clear. If no one would rather swap in their pairs, then it is stable. If no swaps occur, then it is stable. So let's move this over so we can start writing the pseudocode. So starting the pseudocode. So how does the Gale-shapely algorithm work? How does it work? So we first take in a proposer. Let's call them P. So for P and big P. So all the proposers. So this could be A, B, or C, or 1, 2, or 3. So for all those people, so the people who are proposing, the people who propose to some other party. Let's call them E for acceptors, or, well, even though it's an A, let's use A here actually. Let's just use A, not to get confused with all the A's over here. But in this case, we're just going to talk about people who accept. So for all A in A, so if A over here is proposing, so this in case it will be P, proposes to B, and B in this case would be A, and this would be P. So all the people who are proposing propose to some person A based on their most preferred to their least preferred. And it goes like this. So this is the first step. The second step is this. If A is unmatched, if A is not matched, A is not matched with anybody. So if A proposes to 1 and 1 isn't with anybody, they just matched automatically. So if 1 doesn't have anybody else matched with, their first match, they get matched immediately. So if A is not matched with anybody, just match with P. Match with P. Else, we have an else here, so else if A is matched, so if A is matched, check if P is better. So if A is already matched, A is going to check their preference list. So A proposes to 1 here, it's a different A. A proposes to 1 here. Now if B comes in and proposes, 1 is going to check their preference list. And if 1 says, I actually like B more than A becomes unmatched. Now, then C goes through and picks whoever they want, and then it loops back over. So, in all, this entire algorithm, runs, so we do this, so all this runs while all big P are unmatched. So are unmatched. So this is going to, so if A becomes unmatched, it's going to loop through the entire algorithm again and then check for each one to check if they're unmatched or not. Because as we loop back over, even though we know A has been unmatched, we don't know if B is unmatched or C is unmatched. So we have to check n items again. So now let's work through an example that we have here on the right. An example we have here on the right. Let's say A proposes first. Let's say A proposes first. So we see that A likes 1. So A proposes with 1. They match. B likes 2. B proposes to 2. They match. C likes 3. C proposes to 3. They match. And that's if A proposes first. That's if A proposes first. Now let's see what happens when B proposes first. When B proposes first. So B is the proposer and A is the acceptor. Now let's see. So we first have 1 proposes to A. 1 proposes to A. Now 2 proposes to A. Now it's up to A to choose who they prefer the most. So A is going to check their preference list. And it seems again that A most prefers 1 over 2. So A is actually going to stick. A is going to stick with their match. So 2 cannot choose that anymore. So let's move on to the next one. C. Let's see C. So 3 proposes to C. 3 proposes to C. 3 proposes to C. Now we're gonna loop back up to the top. We're gonna check 1. Okay, 1 has a match. 1 has a match. 2. We're going into 2 again. We're gonna see. Okay, 2 is now going to propose to B. 2 is now going to propose to B. B is unmatched. And now that's the stable matching. So there are some claims with this. There are some claims that in every run of the Gale-shapely algorithm that there will always be a stable matching. There will always be a stable matching. No matter what happens, no matter how these tables are set up, there will always be a stable matching. And as if you caught it while we were running it, the side who proposes first, the side who proposes first gets their best choice. As we saw with the first run, no matter what B's preference list was, when A proposed first, A got exactly what they wanted. It's only when we have things like conflicts where the accepting side gets to choose who they prefer. In this case, A preferred B. Only when there's a conflict. So the side who proposes first gets their match, unless there is a conflict. Unless there's a conflict. There's another terminology that we haven't said. There's some more terminology we haven't said. Let's put it right here. Let's expand this a little bit. There's another one where it states a unique stable matching. A unique stable matching. A unique stable matching is when if A proposes and B proposes, if the same matchings occur, so if the same matchings occur whether B or A proposes first, then that is a stable matching. That is a unique stable matching. So a unique stable matching is when the table stays the same no matter who proposes. Not the table, the stay the same. The matchings stay the same. The matchings stay the same. Stay the same, no matter who proposes first. Now, let's talk about the runtime. What is the runtime of this? Now, in terms of big O, we know we have, these are n items for proposers. These are n items, so we know we have to go n times. So we know our big for loop, since we have a while here, we know our big for loop is going to have n. So now we're going to have to iterate n times. And for every for loop, we're going to just check if every person is unmatched. So we know that if A proposes and A loses their match, they'll have to wait till the next round. Or depending on how you set it up, they could keep trying for people. But this might be easier to see it this way. Let's say they have to wait till the next round. Now C proposes who they want to propose to. Now we have to go all the way back up again and check again if each person is unmatched for our algorithm to stop. Now if for every iteration, if one person becomes unmatched each time, again having to check the entire list, that means we're going to have to do another n iterations, so a nested for loop. So that means if every iteration at least one person becomes unmatched, we'll have to do it again for another, we have to check another n participants. This leaves us with n squared. So in the worst case, the Gale-Shapley algorithm runs n squared. And that's the Gale-Shapley algorithm. If you enjoyed the video, don't forget to like and subscribe. For code examples, test examples, and a concise rendering of this video, there is an open source textbook in the description below. Anybody can contribute and add anything they think is necessary or helpful. And with that, thank you.